Alright, guys, welcome to part 2 of chapter 1. Um, this is a pretty long chapter, honestly, and we are starting off with networks defined by topology. If you liked my video on networking for this Network Plus exam, make sure you subscribe, and I'll be posting. I'm going to try 1 to 2 videos Monday through Friday, mainly doing with IT, networking, maybe some coding, cyber attacks that go on. I'm going to be trying to cover anything IT related. I plan on doing some CTF, some other textbooks, just anything IT related. I really enjoy IT, and I want to be something where you're at work, you're playing a game, I'm just off on the side talking to you about IT, and hopefully something sticks with you. But nonetheless, let's get started. Networks defined by topology. In addition to classifying networks based on geographic placement of their components, this was like the WAN, LAN, and all that kind of stuff. Another approach to classifying a network is to use network's topology. Looks can be deceiving, however. You need to be able to distinguish between a physical topology and a logical topology. Physical versus logical. Just because a network appears to be a star topology, which is right here, this token ring, it's shaped like a star. That is, where the network components are all connected back to a centralized device, such as a switch. This MAU is the centralized device. The traffic might be flowing in a circular pattern through all of the network components attached to a centralized device. The actual traffic flow decides the logical topology. I'll say it again. The actual traffic flow decides the logical topology. Logical does not have to do with how it looks, whereas the way components are physically interconnected determines the physical topology. The way the components are physically interconnected, aka how it looks. Call a spade per se. For example, consider figure 1-4, which shows a collection of computers connected to a token ring media access unit, which these are in museums now. No one uses a token ring. From a quick inspection of figure 1-4, you can conclude that the devices are physically connected to a star topology, where the connected devices radiate from a centralized aggregation point, that is MAU in this example. So centralized device, each device going to it looks like a star, meets the criteria for a star, logically, physically, yeah. Going on to the next. Next, contrast the physical topology in figure 1-4 with the logical topology illustrated in figure 1-5 and later in figure 1-8. Although the computer is physically connected to the MAU, when you examine the flow of traffic through, or in this case around the network, you can see the traffic flow actually loops around and around the network. The traffic flow dictates how to classify a network's logical topology. In this instance, the logical topology is a ring topology because the traffic circulates around the network as if circling around a ring. Okay. That would have been helpful to know that here. Before you run out and try and purchase a token ring network, keep in mind You will only see this technology in networking museums, which is what I was saying. I mean, let's go ahead and let's get a Google search on when this came out. Token ring release date 2002. Yep. What came after a token ring? Oh, well, it says introduced 1984. Yeah. Standardized in 1989. Okay. That would be interesting to make a video on. Bus topology. So we are now concluding with the star and ring topology. So for this, the physical was a star and logical was a ring because the traffic circulates around the network just like a ring. Alright, so next, bus topology. And just looking at this straight away, I mean, it's like passengers sitting in a bus. You have this line, a singular link, and then you have each computer. And my guess would be if computer 2 goes out, this might disrupt resource flow going towards all the other computers. But let's take a look. A bus topology as depicted in figure 1-6 typically uses a cable running through the area needing connectivity. Devices that need to connect to the network then tap into this nearby cable. Early Ethernet networks relied on bus topologies. Drinking some green tea. A network tap might be in the form of a T connector used in older 10-base-2 networks, or a vampire tap used in older 10-base-5 networks. Figure 1-7 shows an example of a T connector. Oh, what would you know? It's shaped like a T. Note, the Ethernet standards mentioned here, that is 10-base-2 and 10-base-5, in addition to many other Ethernet standards, are discussed in detail in Chapter 4, Ethernet Technology. A bus and all devices connected to that bus make up a network segment. As discussed in Chapter 4, a single network segment is a single collision domain, which means that all devices connected to the bus might try to gain access to the bus at the same time, resulting in an error condition known as a collision. So when all devices connect to the bus at the same time, that can result in a collision, just like a car collision. Table 1-1 shows some of the primary characteristics, benefits, and drawbacks of a bus topology. They throw a lot of these at us. Let's try and go through these briefly. Characteristics: one cable is used per network segment, just like we were looking at before. Benefits: less cable is needed to install a bus topology because you're only using one cable. Drawback: because a single cable is used per network segment, the cable becomes a potential single point of failure. Single point of failure meaning if one client fails, it can disrupt flow of data or media to the rest on the network. To support appropriate electrical characteristics of the cable requires a terminator at each end of the table. Depending on the media used by a bus topology can be less expensive. And another drawback, troubleshooting a bus topology can be difficult because problem isolation might need an inspection of multiple network taps to make sure they either have a device connected or they are properly terminated. Another characteristic, bus topologies were popular in early Ethernet networks. Network components tap directly into the cable via a connector such as a T connector, which we looked at before, it's shaped like a T, or a vampire tap. Installation of the network based on a bus topology is easier than some other topologies, which might require extra wiring to be installed. But extra wiring usually means more redundancy, which is good. You want that. Some more drawbacks. Adding devices to a bus might cause an outage for other users on the bus. That's a major drawback. An error condition existing on one device on the bus can affect performance of other devices on the bus. That's not good. A bus topology does not scale well because all devices share the bandwidth available on the bus. Also, if two devices on the bus simultaneously request an access to the bus, an error condition results. So yeah, looking like a lot of drawbacks in favor for this bus topology. Let's see what the ring topology has to offer us. So, concluding bus topology. Figure 1-8 offers an example of ring topology, where traffic flows in a circular fashion around a closed network loop, that is, a ring. So a circle. Typically, a ring topology sends data in a circular direction to each connected device in turn until the intended destination receives the data. Token ring networks relied on a ring topology. So let's look at computer 1 right here. Sends a packet of data, sends it to this one, sends it to this one, and let's say this is the destination. But in order to get here, you had to send it to the other two. And basically all the computers are doing this. Doesn't seem very efficient. It would be a lot more helpful to have a connection going here to here, here to here. But, that would be more expensive. Alright, continuing. Token ring, however, was not the only popular ring-based topology popular in networks back in the 1990s. Fiber Distributed Data Interface, FDDI, was another variant of a ring-based topology. Most FDDI networks, which, as the name suggests, have fiber optics as the media, use not just one ring, but two. These two rings send data in opposite directions, resulting in counter-rotating rings. One benefit of counter-rotating rings was that if a fiber broke, the stations on each side of the break could interconnect their two rings, resulting in a single ring capable of reaching all stations on the ring. Because a ring topology allows devices on the ring to take turns transmitting on the ring, contentation for media access was not a problem, as it was for a bus topology. Interesting. If a network had a single ring, however, the ring became a single point of failure. If the ring were broken at any point, data would stop flowing. Table 1-2 shows some of the primary characteristics, benefits, and drawbacks, just like before. So the main difference here, this makes perfect sense. If you look back here, say computer 1 gets eliminated, the worker gets mad and breaks the computer. He's disrupting the flow, because how is this computer going to talk to this computer? He's supposed to go through here. What would need to happen is, and instead of having this hole, you just have to connect the two or fix the one here. That's a major problem. It seems like very likely to happen. Characteristics: devices are interconnected to a single ring or a dual ring. Self-explanatory. Each device on a ring includes both a receiver for incoming cable and a transmitter for outgoing cable. Each device on the ring repeats the signal it receives. By repeat, it's sending it to the next one. Next, we have some benefits. A dual ring topology adds a layer of fault tolerance. Therefore, if a cable break occurred, connectivity to all devices could be restored. Troubleshooting is simplified in the event of a cable break because each device on a ring contains a repeater. When the repeater on the far side of the cable break does not receive any data within a certain amount of time, it reports an error condition, typically in the form of an indicator light on a network interface card, your NIC, NAC, NIC. Well, that's a good benefit. Having an indicator based on time, that could be helpful for a network administrator. Rings have scalability limitations. Specifically, a ring has a maximum length and maximum number of attached stations. Once either of these limits is exceeded, a single ring might need to be divided into two interconnected rings. A network maintenance window might need to be scheduled to perform this network division. So what this is pretty much saying is, if your network gets too large, you have to make another ring. And what this means is, your network is going to be down for maintenance. Just like you're logging on to Call of Duty and the servers are down. That's pretty much what your employees or customers are going to be experiencing. Definitely a pretty big drawback, in my opinion. Another drawback, because a ring must be completed loop, the amount of cable required for the ring is usually higher than the amount for a bus topology serving the same number of devices, which is true. Imagine having a bus topology that has to make another bus topology to wrap itself around. It's basically like a double bus topology, but does offer more redundancy, which is good. Another benefit, each device on the ring repeats the signal it receives. That's self-explanatory. Alright, so concluding ring topology, now we are going on to star topology. Ooh. Figure 1-9 shows a sample star topology with a hub at the center of the topology and a collection of clients individually connected to the hub. Notice that a star topology has a central point from all attached devices radiate and lands. That centralized device was typically a hub back in the 1990s. Modern networks, however, usually have a switch located at the center of the star. It would be interesting to do a video on the differences between hub and switch. But a switch is basically a hub, but more logically proficient. As reviewed in episode 1, a switch identifies which port is requesting and receiving information, which is a lot more efficient compared to a hub, which sends everything everywhere. And please, guys, if you have anything to add, just leave me a comment. Message me in Discord if you want. I'd be glad to hear your opinions. No, Chapter 3 discusses UDP and other types of cabling. Yes, UDP, very important. There's a model for it, and it's very important to the OSI model. Alright, Figure 1-9, star topology. I thought we saw star topology earlier, but here it is again. The star topology is the most popular physical LAN topology in use today, with an Ethernet switch at the center of the star and unshielded twisted pair UTP cable used to connect from the switch ports to clients. So these white squares here are the switch ports, and these ports are used to talk to the clients, which is pretty helpful. Table 1-3 identifies some of the primary characteristics, benefits, and drawbacks of star topology. Characteristics. Devices have independent connections back to a central device, for example, a hub or switch. Star topologies are commonly used with Ethernet topologies. Some benefits. A cable break only impacts the device connected via the broken cable and not the entire topology. Troubleshooting is relatively simple because a central device in the star topology acts as the aggregation point of all the connected devices. A couple of drawbacks. More cable is required for a star topology as opposed to the bus or ring topology because each device requires its own cable to connect back to the central device. Installation can take longer for a star topology as opposed to a bus topology or ring topology because more cable runs need to be installed. This makes perfect sense. Go back here, you see each has its independent cable, which is optimal. That's very good. And now we are getting into some, looks like WAN technology. Hub and spoke. These are pretty important to know. When interconnecting multiple sites, for example, multiple corporate locations via WAN links, a hub and spoke topology has a WAN link from each remote site that is a spoke site to the main site that is the hub site. So we have the hub site and the spoke site. This approach, an example of which is shown in figure 1-10, is similar to the star topologies used in LANs. Which WAN links, which are these, a service provider is paid a recurring fee for each link. Therefore, a hub and spoke topology helps minimize WAN expenses by not directly connecting any spoke locations. If two spoke locations need to communicate between themselves, their communication is sent via the hub location. Table 1-4 contrasts the benefits and drawbacks of hub and spoke WAN topology. So you have your hub and then your hub site, spoke site. The key thing to remember here is that these are not connected to each other. That is the big difference. You have one hub and then all of these, which none of these spoke sites are connected to each other. Characteristics. Each remote site that is a spoke connects back to the main site, that is, the hub, via a WAN link. Benefits. Costs are reduced as compared to a full mesh or partial mesh topology because a minimal number of links is used. Communication between two remote sites travels through a hub site. Adding one or more additional sites is easy as compared to a full or partial mesh topology because only one link needs to be added per site. And now some drawbacks. Suboptimal routes must be used between remote sites because all inter-site communication must travel via the main site. That is a big drawback to having one central hub site, of course. Because all remote sites converge on the main site, the hub site potentially becomes a single point of failure. If the hub site goes out, you are out of luck, my friend. Because each remote site is reachable by a single WAN link, the hub and spoke topology lacks redundancy. And by redundancy, that means if this goes out, there is no redundancy. These have nothing to communicate to. Alright, so this concludes hub and spoke topology. Next, we will be going into full mesh topology, which is the ideal topology. Whereas a hub and spoke WAN lacked redundancy and suffered from suboptimal routes, a full mesh topology directly connects every site to each other. Look, you have, say, hub 1. It's connected to every other single hub. This is ideal because if this one goes out, all of these can still communicate with each other. This is a lot different than your hub and spoke topology. Every site directly connects to the other site. An optimal path is selected, and opposed to relaying traffic via another site, a full mesh topology is highly fault tolerant. And by highly fault tolerant, it means there's room for error. By inspecting figure 1-11, you can see multiple links in the topology could be lost, and every site may be able to connect to every other site. True. And some characteristics, benefits and drawbacks, just for the sake of time. Every site connects to every other site. That is probably the biggest characteristic of full mesh. When you think of full mesh, just think of every site connecting to every other site using a WAN link. Benefits: optimal routes exist. True. A full mesh network is fault tolerant. True. We talked about that. Troubleshooting a full mesh network is relatively easy because the links are independent. True. And the drawback: a full mesh network is difficult to install and expensive to scale, because think about it. Look at how many links you're using. It's obviously going to be expensive, but it's probably worth it because these benefits are pretty good. I think it's worth the money. But yes, being expensive is what you think about when you hear full mesh. Alright, now we have partial mesh. A partial mesh WAN topology, as depicted in figure 1-12, is a hybrid of the previously described hub and spoke topology and full mesh topology. Specifically, a partial mesh topology can be designed to offer an optimal route between selected sites while avoiding the expense of connecting every other site. So let's take a look at this picture. This one is connected to 4 sites out of the 5. So all of them. Look down here, this one is connected to 1, 2. So this is pretty much the smart full mesh topology. Not every link is connected to every site. For cost reasons, I would assume, almost all the time. When designing a partial mesh topology, a network designer must consider network traffic patterns and strategically add links interconnecting sites that have higher volumes of traffic between themselves. Table 1-6 highlights the characteristics, benefits, and drawbacks. Characteristics, it's pretty self-explanatory. It's pretty much a full mesh where not every site is connected to every other site. It says it's similar to a hub and spoke, which I would disagree to, because every site is linked to at least 2, right? A hub and spoke is one hub and multiple sites, so obviously different. The main benefits is that you have more redundancy, you're connected to more points, it's more fault tolerant. The same benefits as the full mesh, just at a lower scale, and drawbacks. Same drawbacks. It's more expensive than hub and spoke, and is less fault tolerant because not every site is connected to every site. Alright, so to conclude that, we had the hub and spoke, full mesh, and partial mesh. All pretty easy to remember. And now we are moving on to wireless topologies. We have ad hoc, infrastructure, mesh, and yeah. To say that wireless technologies have grown popular of late would be a huge understatement. As such, Three major categories of wireless topologies have been identified, although this section provides a high-level overview of these network designs. Keep in mind that Chapter 8 offers a much greater level of detail. Ad hoc. The simplest of wire topologies is the ad hoc wireless network. This means that the wireless nodes are in charge of sending and receiving traffic to other without the assistance of infrastructure devices such as switches or access points. Some network engineers refer to the ad hoc topology as simply a wireless peer-to-peer P2P type of network. One common example of an ad hoc wireless network would be Apple's AirDrop, used to send files between two smartphones. And if you aren't familiar with how AirDrop works, basically, two people turn on their AirDrop. You want to send a picture, you just click a button and it sends it to the other person. I mean, it's kind of like text messaging. Your Network Plus exam does this as well. The opposite of this approach is an infrastructure topology, which is discussed next. Infrastructure. With the infrastructure topology, you have specialized wireless equipment for permitting the wireless communications to take place. Many homes today feature a wireless local area network, WLAN, a wireless access point, WAP, not the not the the Grammys WAP, wireless access point, allows the various computers and other wireless devices to communicate with each other through the WAP, acting like the hub device. This WAP connects to the service provider, SP, of the home user with a wired connection. For example, a coaxial cable could connect to the broadband cable service for high-speed internet connectivity. All very true. Mesh. A specific type of ad hoc wireless topology is the mesh. This topology is more sophisticated than the ad hoc in that specialized nodes help move the traffic throughout the topology. Note that these devices are not fancy as the access points found in an infrastructure type of topology. The first wireless mesh topology I ever had the pleasure of working on was one that could adequately provide coverage for a large recreational vehicle RV park. Obvious challenges with this design came in the form of interface and the nodes' ability to sustain the harsh environmental conditions often found in Florida, USA. Yes, that would be the sun and occasional tropical storms. And hurricanes, true. Networks defined by resource location. Yet, another way to categorize networks is based on where network resources reside. An example of client-server network is a collection of PCs all sharing files found on a centralized server. However, if those PCs had their operating systems, for example, Microsoft Windows 10 or Mac OS X, configured for file sharing, they could share files from one another's hard drive. This is referred to as peer-to-peer network. Because the peers, the PCs in this example, make resources available to another peers, the following sections describe client/server and peer-to-peer networks in more detail. And next we have client/server networks. And in this picture you have a file server. I'm assuming this is like a hub or a switch. and your printer, your client, and client. Figure 1-13 illustrates an example of a client/server network where a dedicated file server gives shared access to files, and a networked printer is available as a resource to the network's clients. Client/server networks are commonly used by businesses and schools because, I remember seeing this in school, because resources are found on one or more servers. Administration is simpler than trying to administrate servers or trying to administer network resources on multiple peer devices. So pretty much everything has its own link to this server. And then you have your file server where the person here is in charge of, setting up the passwords, group policies, all that kind of stuff, system administration. He's in charge of setting all this kind of stuff. And for some reason, setting up a printer to a network is very difficult. If you know how to set up a printer to the network, you're already ahead of the game, honestly. Alright, so the performance of a client/server network can be better than that of a peer-to-peer network because resources can be located on dedicated servers rather than on a PC running a variety of end-user applications. You can simplify backups because fewer locations must be backed up. However, client/server networks come with the extra expense of dedicated server resources. The table 1-7 contrasts the benefits and drawbacks of clients/server networks. Alright, so let's get into this table. Characteristics. Alright, client devices, for example PCs, share a common set of resources. For example, file or print resources located on one or more dedicated servers. Resource sharing is made possible via dedicated server hardware and networking operating systems. Benefits. Client/server networks can easily scale, which might require the purchase of additional client licenses. Administration is simplified because parameters, such as file sharing permissions and other security settings, can be administered on a server as opposed to multiple clients. Drawbacks. Because multiple clients might rely on a single server for their resources, the single server can become a single point of failure in the network. Client-server networks can cost more than peer-to-peer networks. For example, client-server networks might need the purchase of dedicated server hardware and a network OS with appropriate number of licenses. And they got 2 notes for us here. A server in a client-server network could be a computer running a network operating system, an OS, such as a Linux server or one of the Microsoft Windows Server operating systems. I'm actually familiar with this Microsoft one. I can set up a video one day if anyone is interested in that. Alternatively, a server might need a host making its file system available to remote clients via the Network File System Service, which was originally developed by Sun Microsystems. Interesting. Note. Okay, our next note. A variant of the traditional server and a client-server network where the server provides shared file access is network-attached storage, NAS. A NAS device is a mass storage device that attaches directly to a network rather than running an advanced NAS. Alright, sorry guys, I had some business to attend, so let's get back to the second note. A variant of the traditional server in a client/server network, where the server provides shared file access, is a network attached storage, NAS. A NAS device is a mass storage device that attaches directly to a network. Rather than running an advanced NOS, a NAS device usually makes files available to a network client via a service such as NFS. Alright, now we are heading on to peer-to-peer networks, which is something pretty common you'll see. Peer-to-peer networks allow interconnected devices, for example, PCs, to share their resources with one another. Those resources could be, for example, files or printers. An example of a peer-to-peer network, consider 1-14. Okay. Where each of the peers can share files on their own hard drives, and one of the peers has directly attached printer that can be shared with other peers in the network. Wow. So what's the difference? No file server, no network printer. The printer is a part of this peered device. Peer-to-peer networks are seen in smaller businesses and in homes. The popularity of these peer-to-peer networks is fueled in part by client operating systems that support file and print sharing. Scalability for peer-to-peer networks is a concern, however, specifically as the number of devices, that is, peers, increases, the administration burden increases. For example, a networked administrator might have to manage file permissions on multiple devices, as opposed to a single server. That means more work for a network administrator. Consider the characteristics of peer-to-peer networks as presented in Table 1-8. Characteristics. Client devices, for example PCs, share their resources, for example file and printer resources, with other client devices. Resource sharing is made available through the client's operating system. Some benefits. Peer-to-peer networks can be installed easily because resource sharing is made possible by the client's operating system, and knowledge of advanced NOSs is not required. Peer-to-peer networks usually cost less than client-server networks because there is no requirement for dedicated server resources or advanced NOS software. Drawbacks. Scalability is limited because of the increased administration burden of managing multiple clients. Performance might be less than what is seen in a client-server network because the devices providing network resources might be performing other tasks not related to resource sharing. For example, word processing. And we got ourselves a little note down here. Some networks have characteristics of both peer-to-peer and client-server networks. For example, all PCs in a company might point to a centralized server for accessing a shared database and a client-server topology. However, these PCs might simultaneously share files and printers between one another in a peer-to-peer topology, such as a network, which has a mixture of client-server and peer-to-peer characteristics, is called a hybrid network. Alright, thank you for that note, and we got ourselves a little real-world case study, which we love these. These help us put our knowledge to the practical world. Alright, let's get ready. The headquarters for ACME, 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 I don't know, Inc. is located on a single floor of a downtown building. Acme also has two branch offices, Branch 1 and Branch 2, that are in remote locations. The company wants to do file sharing, instant messaging, email, and voice on its own private network when possible. It also wants connectivity to the internet. At the headquarters location, they set up a LAN with UTP, remember that is the cable, and in this instance they are using UTP Cat5. Cat stands for category. UTP Cat5 cabling, with the clients and servers connected to a central switch. This forms a physical star topology. For connectivity between HQ and its two branch offices, the company uses a service provider, SP being service provider, for WAN connectivity. The SP provides logical point-to-point connections between the headquarters office to both of the branch locations. Physically, the path between the headquarters to each of the branch office is going through several routers in the SP's network. For the time being, Branch 1 and Branch 2 do not have direct connectivity to each other, so branch-to-branch traffic must pass through the headquarters site, hub and spoke. And if you don't remember hub and spoke from earlier, the hub and spoke is a WAN topology where you had the one hub that branched off to the 5 spokes, the one that lacked redundancy. Next year, as more funds are available, the company can add WAN connectivity directly between Branch 1 and Branch 2. This will change the WAN topology from hub and spoke to full mesh. Wow, they are skipping the partial mesh and going straight to full mesh. Wow, that is pretty crazy. Alright, and it looks like we are done with Chapter 1. Wow, congratulations on making it this far. You are 1 chapter out of 15 away from passing your exam. Summary. The main topics covered in this chapter are the following. Introduce you to various network components, including the client, server, hub, switch, router, media, and WAN link. True, and true. One way to classify networks is by their geographical dispersion. LAN, WAN, CAN, MAN, PAN, WLAN, and SAN. True, and true. Another approach to classifying networks is based on networks topology. Examples of network types based on topology include bus, ring, star, partial mesh, full mesh, and hub and spoke. This text also provided information on various wireless topologies available. And we also talked about client, server, and peer-to-peer networks. So we covered a whole lot in this first chapter. I really hope you guys are learning from this. If you are confused, I would go back to the video, put this on 2 times speed, listen while you're at work, listen twice. Do what you need to do some outside research, Google is your best friend. Do what you need to do to understand these topics. Yeah, we can go ahead and skip this for now. And here are some review questions. I'm not going to go over these myself because this is already a pretty long video, but I will go ahead and scroll through these. Traffic forwarding decisions on MAC address, hub. These are pretty self-explanatory. A network formed by interconnecting a PC via USB. That's the personal network. These are all very easy. Which physical LAN topology requires the most cabling? That would be the star. Bus? No. Ring? Possibly. Ring has more than bus. WLAN? No. So I would say star or ring, most likely star. So yeah, pause the video, go Go through these if you want. They are great practice. And, yeah. Chapter 2, OSI model. This is probably my favorite chapter. I love the OSI model. But this video is getting too long. We will save that for video 3. Chapter 2, episode 1. If you guys enjoy this, subscribe. I will be doing all the chapters. So yeah, I hope you enjoy. Comments, questions, concerns, leave them down below. Leave a like and subscribe. Thank you guys.